Hello all. Today we're going to learn how to compute sign of integer using bitwise operations. Now, why to do bitwise operation? Because again, it's a concise code and it's a faster code than your normal if-else logic. So let's see. I'm going to show two variations of it. So let's start with the first one. Uh, to understand that, you need to know how a positive and a negative number is stored in memory. So positive, like everyone knows, it's a binary representation, right? One thing to notice is that the most significant bit is the sign bit. Okay, so I'm going to take example with 4 bits here. So let's say we have +5, how this will be represented. So 1 2 3 4 and 101, right? And this one is the sign bit, so this one would be 0. What about -5? So what happens in case of -5 is that this bit would be, this is the most significant bit, right? This one would be 1 always, and then we represent 2's complement of 5 here. And how do we do that? So to compute 2's complement, you first just write the binary version of 5, and then what you do, you make 1's complement first, okay, which would be in this case just switching the bits. So 0, 1 and 0, and then you add 1 to it. Is a binary addition. Okay, so if we add 1, so 1 and then 1 and then 0. So if you see now, this would be representation here. So 0 1 1, so this is -5. Okay, so that's how positive and negative numbers are stored in memory. Now let's see, how can we compute the sign? So now we know this bit is the sign bit, right? So what we can do is we can use a right shift operation to take this bit here, okay, or in this case this bit here, okay, and then we'll see. So here is the logic to do that. So we'll do sign equals v right shift, and then how many times? Size of int, okay, and then times 8 and then -1, okay, these many times. Let's try to run this, try run this in one of the examples. So for example, let's say this, let's take this case +5, okay. What happens +5 for +5? So +5 is 1 0 1 and 0. So we do how many times? Let's say size of int is 4 bytes, so 4, okay, so here like I'm taking example for 4 bits, right? So in our case, so the idea is essentially to do, so for example, if the size of integer in the machine is 4 bytes, then this would be doing it 31 times. 4 into 8 minus 1, right? In our machine, is just 4 bits to represent the integer. So what we would do is, going by this formula, it would be like 3 times, okay. So what we would do is do a right shift operation 3 times. So what happens when the first time? So what happens is this one goes, gets lost. This one moves here, this moves here, and this moves here. And what happens here is like whatever bit is here gets copied. So, okay, so what happened? What would be the next version here? This gets here, so 0, and then this one moves down here. So 1, this one moves down here, so 0 and then 0, okay. And then one more time would be again same thing. This one gets lost, then this one moves here, 0 0 and then 0, okay. Next iteration, the last one, this one gets lost, so 0 and then 0 0 0, okay, everything is 0. So sign would be equal to 0, right? Sign becomes 0. So in case of, so we can say that if a number is greater than 0, the sign equals implies 0. So if this calculation gives me 0, I know that it's a positive number, okay, although there is a catch with 0, but we'll consider that case later. Let's take the example of -5, okay. So -5, we already computed how it would be represented, right? So this is the representation of -5, 1 0 1 1, right? So let's take that. So -5 is equals 1 0 1 1 in binary, okay. What we'll do, we'll again like do the right shift 3 times. So first iteration, uh, this bit gets lost. So and all of these will move one position to the right. So 1, this moves here. So 0, this moves here, 1, and now this bit gets copied here. Okay, so it's 1. Okay, so this is the first iteration. Now next one, this gets out of the window. This moves here, 0, 1, 1, and 1. Okay, so this is the last one. So this gets out, this 0 gets out. So 1, 1, 1, and then 1, because in this case, like 1 is getting filled from the left. Okay, so this is, so sign equals this. Now what is this number? How to know what is this number? So as I said, the most significant bit is the sign bit. Okay, this is the sign bit. So if it's 1 in the system, that means it's a negative number. Okay, and what is the value of that number? So we'll take the remaining 3 and do 2's complement. Why? Because we know that negative numbers are represented as 2's complement. So let's do the 2's complement for 111. So what happens? 111, we do 1's complement. So we will just flip the bits and then we'll add 1. Okay, so plus 1. So what happens? 0, 0, 1. Okay, and then so essentially this is the representation, 1 and then 0, 0, 1, which is equal to minus 1, right? Because this gives me 1 and this sign bit gives me minus, so this becomes, so I know sign is minus 1 here. So what we saw, in case of positive number we got 0, right, in the sign variable, and in case of negative number we got minus 1, right? What happens in the case of 0? So if let's say my number is 0, what happens then? So 0 is represented as 0, 0, 0, 0, right? If we do all the shift, it would still be 0, 0, 0, right? And so sign becomes 0, right? Sign becomes 0 after all the operation. So for 0, the sign becomes 0. So for 0, so what does this logic gives us now? For 0 and greater than 0 numbers, sign would be equal to 0, and then for less than 0 numbers, sign would be equal to minus 1, right? So that's what this logic gives us. What if we don't want that? Like, what if I want a sign to be um, plus 1 for greater than 0 numbers and minus 1 for less than 0 numbers, and maybe greater than equal to 0. Let's stick with that, with this, for this version. So for greater than equal to 0, we would say I want the sign to be plus 1, and for less than 0 we want the sign to be minus 1. Okay, so how can we modify this formula? Okay, so what was the formula? Let's take it again. So num right shift. So here we are doing it 3 times, right? So the logic is then that what I'm going to do is I'm going to add bitwise OR it with 1. Okay, and this I'm going to store in my sign. Okay, so how this will work? So let's take example of a positive number. Okay, so let's say plus 5. So let's say num equals plus 5. What happens? So again, 1, 0, 1, 0, and then you do right shift 3 times. So after right shifting 3 times, what happens? Um, Everything gets lost, right? So this bit would move to this position, and then everything would be 0 here. And then what we are doing is we are doing a bitwise OR with 1. So bitwise OR with 1 works like this. So every bit would be ORed with 1. So 0, 1 would be 1, and then 0, 0, 0. Okay, so this means 1. So sign would be 1 in this case. Okay, uh, previously it was 0, right? So now we got this. What about minus 5? If num equals minus 5, then what happens? So let's see. Let's again see what is the representation of minus 5. Let's copy it from here. What was our minus 5? 1, 0, 1, 1. Okay, so 1 0 1 1, this is my binary representation for -5, right? I'm going to right shift it 3 times according to my logic. What happens is uh, this one this one moves here, and then all the bits are 1 now, right? And then what I'm going to do is like I'm or like I have to do a bitwise OR with 1, right? So 0 0 0 1. So what happens now? 1 1 would remain 1, okay, and then everything would be 1, right? Uh, so now what happens? What is this number? What is this number in this memory? So we learned that this is the sign. So this, if it's 1, it's a negative number, right? And again we do 2's complement of this one. This one would give me how much? Let's compute. This one would give me 1. How? So we'll switch on the flip all the bits first. So 0 0 0, and then we'll add 1, right? So 0 0 1. So this becomes 1, and because the sign was this sign bit was 1, so this is essentially -1 in memory. So we saw this formula gives me -1 for less than 0 numbers and +1 for 0 and above. Okay, so let's try this out in a program. Okay, so here is the program. So I have, so the first, this is the first version, which would print 0 for positive and -1 for negative. Okay, 0 for positive and 0, 0 and -1 for negative, right? So this is, I'm taking this b is 5, and then size of v, I could have directly written 13 or 31, but this is safer because size of integer might vary in different systems. So and then I'm just printing the sign out here, okay, and then I'm taking a negative number, -5, and then I'm doing the same operation, okay, using the same logic, and then I'm printing the sign, and then at last, like, I'm using 0. Okay, so let's compile this and run this, and let's see. Okay, so as you can see, sign of positive number is 0, using this logic. And negative is -1, which is fine, and 0 for 0, we printed 0. Okay, now let's try out the other logic. Okay, let's see. So what I'm going to do, I'm going to comment out all this, and then I'm going to uncomment this part. All right. Oh, sorry. So +1 for positive and 0, 0, and -1 for negative. Okay. Let's try to run this one, and then the formula is different, right? Like, I'm doing a bitwise OR with +1. So let's see what we get for positive and negative numbers. Okay, so v is not okay. So because I commented out, I have to create it here again. That's fine. Okay, that's fine. Let's see. So sign of positive number now becomes 1. Negative is -1, and sign of 0 is 1. Okay. So this one, again, the logic could be further modified based on the requirement. So if you want, like, to consider the case of 0, because it's neither a positive nor a negative number, you want to print, let's say, 2. So you could try that. Okay, so I would leave that as an exercise for you. So try that and let me know in the comments. Thanks for watching.